So today we are supposed to cover the fourth one, and then we move on to the next few topics according to what I have outlined in the group chat. So before we go into the final postulates, we look at what we call as a phase. I hope everyone can see my screen and listen to what I say. Okay. So what is a phase? A phase basically is this particular term. So where this particular term locates actually can affect certain things. So the first one is what we call as a global phase factor. So if it is a global phase factor, it means that you can attach to your quantum states and it doesn't really affect your measurement statistics because when you so let's say this is your POVMs, this is your measurement operator, and uh, the way it works, the way this particular phase works is that you have to act on your cat, and then you also have to act on your bra. So in this case, you need to do the complex conjugate. That's why you get a minus. Um, sorry. So that's why over here you get your complex conjugate version, and then over here you get your cat version. So in this case, these two terms they are just values. So you can sort of like factor it out, and obviously when you multiply them together, they just cancel it off. So in the end, you get something like this. So as you can see, global phase factor it doesn't really affect your measurement statistics. So which is why whenever you have a global phase, basically you cannot detect it using any type of measurement. So for this particular reason, we always say that the quantum states is equivalent up to a global phase. So this is how we will write it. And because of this, when you look at your quantum states, you have to normalize it to um, the length has to be equals to 1, the inner product has to be equals to 1. So in this case, your global phase actually adds nothing to it because you can consider this as a complex scalar. So if your vector points towards this direction and your EI theta basically it doesn't really add to your scalar multiplication, it still contributes to this particular direction. So it doesn't really add to the length of your vectors and it doesn't really change the direction of your vectors. So because of this equivalence, we usually say that the real quantum states actually is the rays inside the complex vector space. So then you can sort of like factor out one of these complex number out, and it will still give you the same quantum state. But there is another type of phase which we call as a relative phase. So this is a term, it's the same term, but now it attached to your probability amplitudes instead of multiplied into your whole quantum states. So in this case, if your original state is given by alpha psi alpha plus beta psi beta, so your relative phase multiplies inside one of the probability amplitudes, and you cannot really factor this out because uh, the phase between alpha and beta, it always keep having this kind of relative phase of e to the power of I theta. So in this case, we say that relative phase is a basis dependent concept, and it will give rise to some differences in your measurement statistics. So one of the very good example is you look at the plus and the minus states. So the relative phase difference is only at your one state. So one is plus one is minus one. And when you convert it into the plus and minus basis, which is why it's called a basis dependent concept, when you convert it to the plus and minus basis, and you try to measure in terms of the plus and the minus measurement operator, you will find out that they will give you different measurement statistics. So they are not the same up to a relative phase shift. So this is the differences between a global phase vector and a relative phase. So why is this important? You see. So now let's look at the idea of one qubit. So when you have one qubit, um, our Hilbert space, as we know, is given by C2, and this is how we would write our one qubit states. So psi alpha and psi 0 and psi 1, they are complex numbers. So you can write something like A0 plus I B0, A1. So if you write in this way, and because of this normalization condition, so you have A0 squared plus B0 squared, A1 squared, B1 squared equals to 1. So this comes from your normalization condition. So because of this equation, right? So initially you have 4 real parameters, or we can sometimes call this as a degree of freedom. So initially you have 4, but now because of your normalization condition, you minus 1. So you can also minus another degree of freedom because of your global phase vector. So the way you write your quantum state, you can do it as if the first term is a real number, and then only the second term is the complex. Because basically you can factor out one of the phase. So like for instance, if this one is R0 EI theta 0, this is R1 EI theta 1. So I write two different ways of writing your complex number just to show you that how you can remove one of your constants away. So if you do in this way, then R0 squared plus R1 squared equals to 1. This is one equation. The second one would be that you can factor out, let's say, EI theta naught, so that eventually your state becomes R naught 0 plus R1 EI theta 1 minus theta 0 1. So this particular state is still the same state because of the previous equivalence. So we know that when you factor out one of the global phase, it will give you the same measurement statistic, and which is why we can do that. So when you do this kind of maneuvers, you are actually living with 2 degrees of freedom only, and there is one way for us to parameterize this particular one qubit states. The way we do it is to make use of sine and cos. And then the first term, as I said, is a real term. The second one will be a complex term. And the complexity over here is given by your EI phi. So you might question, why do we need to parameterize in this particular way? So I will explain it. So before that, do the calculations. If you have a Pauli matrix, uh, so Pauli matrix is given by this. Find the expected values of Pauli x, y, z with equation 53. So specifically, I need you to find out what is 54, 55, and 56. So I will give you like 10 minutes to do it. So I will discuss one example at 10 p.m. Don't cheat with the answer. Try to do it.
Okay.
So this is the first one. Psi X psi Um, so until this point, when you multiply them together, you should get e minus I phi sine theta over 2 cos theta over 2 plus ei phi. So remember that sine theta, sorry, sine 2 theta equals to 2 sine theta cos theta. So that's why you can factor out um, sine theta. Okay, so in this case, let's write in terms of that. So that's why I get sine theta multiplied with half. Then inside you have ei phi plus e minus I phi. So this will give you cos phi. If you do the same thing, the second one should be sine theta, sine phi. And if you do everything correctly, the last one should be cos theta. So as Jianhao said, next slide has the answer. But the state basically is the same. Just multiply accordingly. You should be able to get the answer using identities like this. So as you can see, the expected values for your Pauli matrices, they actually correspond to your spherical coordinates when your radius equals to 1. If you don't know your spherical coordinates, you just need to multiply r in all these three terms. But because your radius equals to 1, so your expected value for your Pauli matrices actually gives you the spherical coordinates. And that's why sometimes we also write in this way. You can write a dot with the sigmas. So your a is 3-term. You consider your a as a vector, and then your sigma as another vector, which is your sigma 1, sigma 2, and sigma 3. So sigma 1 is your Pauli x, sigma 2 is your Pauli y, sigma 3 is your Pauli z. And just by performing this kind of rewriting these values, you basically get back your block sphere. So there is one thing in particular that I want to point out. The first thing is, why should we write in the double angle formula? So half of the angle. So, or rather, what is the consequences of writing in theta divided by 2? So, as we all know, the 0 states and the 1 states, they are orthogonal to each other when we write in equation 53. But when we represent it as a block sphere, you need to multiply the angle by 2. So theta divided by 2, it becomes theta. And that's why if you look at your 0 state and your 1 state, they are not 90 degrees, but rather 180 degrees because you need to multiply by 2. So similar with your x and y. And your phi is actually like, I don't know what is this name. I forgot the name. But it's just rotation in this way. So it keeps like 360 degree, but your rotation for your theta is only 180 degrees, and it will cover the whole block sphere. There is actually a more sophisticated mathematics, but we will go through it later when we have enough foundation, I guess. So now let's cover a little bit of the last part of your fourth postulate. So the first one tells you where is your state space, or sorry, what is quantum states and where the quantum states lives in, which is your Hilbert space. The second postulate tells you how to evolve your quantum states in a closed quantum system. The third one tells you about the measurement of quantum states. Now the fourth one tells you how to combine um, different quantum states together. So this is what we call as a composite quantum system. And the mathematical way to write it down is by tensor product. So what you can do is to write your states like this. And let's say if your first quantum states is in Hilbert space 1, this is in Hilbert space 2 until Hilbert space n, then this belongs to something like this. So if you are curious again how to perform the tensor product, you can refer back to the linear algebra slides. So like I said, postulate 4 tells you how to combine your composite quantum systems, and it actually allow us to define what is called the entanglement. So suppose you have two qubit states. The first one is given by qubit A, for example. So the Hilbert space A is labeled by HA. Second one would be HB. So let's say the Hilbert space, the two qubit states psi AB uh, is being labeled as psi AB. So they will be entangled if you cannot write in this way. So this is a little bit abstract, but you can try to formulate some examples. So let's say you have this kind of two qubit states where whenever you see this is equivalent to um, the zero state tensor with zero states, and usually the position determines which is A, which is B. So we don't. This is a short notation for a lot of the quantum information or quantum computer scientists try to use. So what you can do is to factor out the first qubit. So as you can see, the zero states, you have both 0 and 1. So you factor out the zero states and then both 0 and 1. Similarly with the 1 state with 0 and 1. And then you can further factor out because the first term and the second term both contains this term. So what you can do is to further factor out the tensor product. And in the end, you see that this is just the plus state, tensor is the plus state. So because your psi AB can be written as something like this, that's why this is a separable state. But it might not be obvious to you how to separate out the states if the states are being a little bit more complicated. So in this case, what we can do is to identify what we call as the separability conditions. So one way to do it is to assume that your states are separable. Sorry, this is a typo. Later on, I need to fix that. Um, so if you assume beforehand a very general state coming from the first qubit A and a very general state coming from the second qubit B, so you assume that this is a separable state by expanding everything. So now you do the expansion, and then in the end you get a state like this. So now you can try to compare and contrast. So you notice that the first term over here, when you multiply with the last term over here, the probability amplitude gives you psi naught phi naught. psi1, phi1. Now you multiply these two together, you get back the same thing. So because your initial assumption is that this is a separable state, so it means that um, when you multiply a very general two qubit states, the probability amplitude of 0, 0 and the probability amplitude of 1, 1, when you multiply them together in this way, and they are equal to the probability amplitude of 0, 1 and 1, 0 multiplied together, if this equation is true, then your two qubit states is separable. If they are not equal, then it is entangled. So this is one way for you to quickly identify um, whether or not your two qubit states is entangled. So then you can quickly test, like for example, if you have a Bell state. So this is one typical example of a Bell state. When you multiply them together, psi 0, 0, psi 1, 1 gives you 1 over 2. And then psi 1, 0, psi 0, 1 is 0. So it's not equal. So that's why your Bell state is entangled. So you can repeat this procedure for 3 qubit states and so on. But you can also see that, let's say you have a 3 qubit state, then you need to assume another one. So let's say something like this. Then you need to perform the multiplication and identify all the possibilities, and it keeps on growing and growing. So this is also not a very efficient way for you to identify whether or not the states are entangled or not. But this is one way for you to do it. And at this point, it is good enough for you to know this. So, what can you do with this kind of information so far? So the first application is, of course, what we can say about super dense coding. Uh, so super dense coding basically asks a very specific question. If let's say Alice and Bob shares an entangled state, so can Alice communicate uh, a certain number of classical bits by just sharing a very small number of qubits? So in this case, in this particular example, let's say Alice and Bob shares a Bell state. So Alice wants to send two classical bits by sharing one qubit. So can you do it? So the answer is yes. So initially, Alice and Bob shares a pair of qubits in the Bell state. So this is the Bell state. So Alice take one qubit, let's say qubit A, and then Bob takes one qubit B. So it means that before the communication begins, Alice and Bob has to share a pair of qubits in the Bell state. They are already entangled. So what Alice needs to do is, if she wants to send 0, 0, she does nothing. If she wants to send 0, 1, she apply Pauli Z on her own qubit. If she wants to send 1, 0, she apply X, and 1, 1, she applies IY. So now let's look at what happens. So initially, 0, 0, you don't need to do anything. So it become the original Bell state. 0, 1, you apply your Z gate. So in this case, what you are actually applying is Z1 identity to your Bell basis. Identity because Alice do not have access to the Bob's qubit. Alice only has access to her own qubit. So that's why the Pauli Z only applies to her qubit, and Z is something like this, right? So whenever you have 0, you do nothing. Whenever you see 1, you change to -1. So therefore, it becomes 0, 0, minus 1, 1. And you can try applying Y1 identity 2 to the original Bell state. And here, sorry, this is the next one. This is X1 I2. You find that it goes back to all these states. So after Alice performs whatever she wants, she then sends her qubit to Bob. And then when Bob has access to both of the qubits, he will perform what we call as a Bell basis measurement. So if you can't recognize by now, um, this 4 basically is the Bell basis. You can perform a Bell basis measurement to decide which one of these Alice actually sent. So what is the benefits of doing this instead of just sending out 2 classical bits to Bob? The benefit is that if let's say this is Alice, this is Bob, and they all have qubit, 1 qubit. If Alice directly send the classical bits to Bob, if someone, we usually use the term if manage to intercept the information, then directly ifs will know what Alice tried to send, right? But now if let's say Alice tries to send the qubit to Bob instead of a classical bits, because if only have access to Alice qubit, so if let's say ifs manage to intercept the information Alice try to send to Bob, so if only have access to qubit A, she doesn't have access to qubit B. So in this case, whatever measurements that the ifs try to do, she cannot really decide which one of the following is actually being sent to Bob, because it will be maximally mixed. Uh, if you don't understand what is a maximally mixed state, you have to wait until at least the next class and how to do partial trace before you can understand that. But let's take my word for it. At this point, let's just believe it that this is true. So as long as you are sending quantum information or like the qubits, the physical process actually prevents you from accessing to what kind of information that Alice sends to Bob, as long as the if does not have access to both Alice and Bob's qubit using superdense coding. So this is the advantage of using quantum communication in this case. So also at this point, I just want to briefly introduce um, how can you actually create a Bell state and measure a Bell state. So the way for you to create a Bell state, usually when you look at your Qiskit, okay, if you are using Qiskit, usually when they initialize their quantum state, it's always at the ground state, which is a 0, 0 state. So in this case, let's say you have something like this. So what we are writing is actually the 0, 0 state, or what we call as the tensor product state. Okay, so the way we read the quantum circuit is actually by sequence. So let's say this is time t0. Then we know that over here, this is 0, 0. and then we have T1. So the Hadamard gate only acts on the first qubit and it doesn't act on the second qubit. So in this case, you have hash 1 tensor with identity 2 0 0 on your T1. So in this case, what it actually does is convert the first one to plus state, second one to um, still the zero state. And then this is what we call as the C naught gate. So then you analyze what happens at T2. Basically, what is a plus state? It will be 0 plus 1 tensor with 0. So the C naught gate, what it does is that it uses the first qubit to control what happens to the second qubit. If the first qubit is 0, then it does nothing to the second qubit. If the first qubit is 1, then the second qubit you apply a NOT gate. So then if you apply a C naught to this whole gate, so what it does is when it is 0, it does nothing. That's why you get 0 0. When it is 1, it flips the second qubit. That's why you get 1 1. So this is how you would create what we call as the Bell state by using a C naught and a Hadamard gate. Okay. So now, how do you perform your Bell basis measurement? If you notice, you are actually doing the reverse process. And it is the reverse process because let's say you have your C00. I forgot what is the corresponding Bell basis, but let's say you have psi plus psi minus. So I forgot exactly what does it correspond to. But the idea is that you try to write your two qubit states into your Bell basis by having some coefficients over here. And as you can see, each of these Bell bases, when you apply your C naught and then Hadamard, it actually goes into the reverse. So then it becomes back to your computational basis with your C11, C10, and so on having a certain probability. And by doing this, when you perform the measurement, you look at what is your A and your B. Let's say if you get 0, 1, then you can check correspondingly what would be the Bell basis for this type of measurement. So you will observe this type of Bell basis combination later on quite a lot, especially when you do quantum teleportation. You also make use of this kind of relationships. So trying to break down into Bell basis, and then you revert back to identify what kind of information that you actually want to send. So this is quite a common tricks for a lot of the quantum computing processes. I will just stop here for today. You want to ask something?